Hello everyone. Today we'll be starting with a series on linked lists. So in this video, first I'll be explaining the basics of linked list, and then we will discuss the time complexities for the different operations on a linked list, and finally we'll write down some code for the same. In subsequent videos, we will be discussing various practice problems on linked list as well. So let's get started. Now, linked list is nothing but a list of nodes where each node holds some kind of information and a reference to the next node in the list. So, this is how a basic linked list looks like. So, each of these cells is actually called a node. Each node holds certain information. So in this case, the information is nothing but an integer, but this could be another structure or a class. So each node kind of stores some kind of an information and also a reference to the next node in the list. So this arrow basically represents that reference. So each node points to the next node in this linked list, which is represented by this arrow. Now you may think that this can be achieved using an array as well. What is the difference? The main difference between an array and a linked list is that an array is stored in contiguous format in memory, whereas a linked list is not. So what do I mean by this statement? So to understand this, let's take an array. Now for an array, we always know the address of the first cell or the base cell. So let's say the first cell is stored at an address x, and we assume that it is an integer array with integer being 4 bytes. So the storage capacity of an integer is 4 bytes. Then we can easily say that the second cell will be present at x plus 4 address, and similarly the third cell will be present at x plus 8. This will be present at x plus 12, and so on. Due to this property, if we just store the address of the first cell, we can easily reach any cell in O1 time, because we can use a simple formula to calculate address of any cell from the base address in just O1 time. That is the reason that accessing cells in an array is just a O1 operation. So since we know x and we can calculate the address of any cell, we can in O1 time we can easily jump to that cell, to the location in the memory where this cell is actually stored. This is not the case with a linked list. In a list, each cell or node can be anywhere in the memory. That is the reason we need to explicitly store the reference or address of the next node in each node. Since the node can be anywhere, we use these references to parse the linked list. So in the linked list as well, we just store the reference or the address of the first node, and once we are at the first node, we can use these references to reach to other nodes in the list. And one more thing, the first node is usually referred to as the head. It is a standard nomenclature and we refer this to as the head of the linked list. So if we need to access the sixth element in the linked list, we can't directly access it like we do in an array. Rather, we would reach the first node using the head pointer, then use the reference in first node to reach the second node, then reach third, then fourth, then fifth, and finally we will reach the sixth node. So accessing a particular index in a linked list is no more an O1 operation but a linear operation. So you might wonder that why do we even use a linked list then? Main reason being that we do not need a continuous empty space in memory for a list. If I want to make an array with 1 million records, I do not need 1 million into 4 bytes of continuous space in memory, which might also not be possible every time. And second reason is not so obvious. So while a list makes certain operations inefficient, it also makes certain other operations more efficient due to its structure. For instance, let's try to insert a new element in an array. Let's take an array of size 4, 0, 1, 2, 3, and let the elements in the array be A, B, C, D. Now if we want to insert an element E at position say 1, then what do we need to do? We first have to make a new array of size 5. So this will be the new array, 3, 4, 5. and we would have to move these elements B, C and D one position forward. So D will come here, C will come here, B will come here, A will remain at its position, and E will be inserted at this position 1. Now, as we can see that this insertion is a linear operation because all the subsequent elements had to be moved by one place to insert an element in between. But let's try to add an element in a linked list. Let's represent the above array as a linked list, and that will be A, B, C and D, and each node is pointing to the next node. Now let's try to add a new element E after C. Now to add a new element E, we need to simply make a new node which will store E, and what we need to do is we need to change the references. So C will now start pointing to this new node E, and E will point to D. So just by changing the references, we have actually added a new element in the linked list, and this is a big O of one operation now. The only caveat here is that to reach the older element, that is C, we would need a linear traversal from head, which would add a linear time complexity. But in cases where we are already at the cell, inserting an element is a big O of one operation. So this addition or insertion in itself is big O of 1, but reaching this cell to change the references is a big O of n operation. But there can be other things as well, like we can maintain a hash map where we have the exact position or address of each cell, and using that hash map we can directly land at this particular cell. But yeah, that is a different issue. What I'm trying to explain here is that by using this concept of linked list, we have actually made some operations much simpler or much more efficient. Now, while solving problems, you would very rarely use a list by yourself unless the problem is based on linked lists. Naturally, you will be using an array majority of the times, but in real world scenarios, a list comes in really handy a lot of times. One very famous application of linked list is the LRU cache. So if you understand maps and heaps as well, then you can probably check out LRU cache problem. Otherwise, you can check it out once you are done with maps and heaps. Now in linked list as well, we have multiple variants. So I'll go through a few of them. The first one is your regular linked list. So in this list, it is pretty simple that we have nodes. Each node points to the next node, and the last node points to null. And the first node in this list is referred to as the head. So first node is always referred as the head, be it a regular linked list or any other variant. So this is the structure of a regular linked list. Now moving on to the next variant, which is doubly linked list. So in doubly linked list, every node stores two references. One reference is to the next node, and it also stores a reference to the previous node in the linked list. So this is how a doubly linked list look like. There are nodes in the list. Each node points to the next node, and the last node points to null. At the same time, each node stores a reference to the previous node as well. So the last node will point to the second last node, the second last to the third last, and similarly so on. In this list as well, we store the pointer to the first node, which is referred to as the head. Now, what is the advantage of a doubly linked list over a regular linked list is that in a regular linked list, we can only move in forward direction. So when I'm at particular node, when I'm at this particular node, I can only move to this node. I cannot move to a previous node. When I'm at this particular node, I can only move to the next node. There's no way I can go to the previous node. But in this particular linked list, I can move in both directions, forward and backwards. So which comes in really handy in a lot of situations. And in this particular list, we sometimes also store the pointer to the last node, which is referred to as the tail. So this helps in traversing the linked list in a reverse fashion. Now a next very common variant of linked list is a circular linked list. So in this particular linked list also, we have nodes. each node points to the next node, but the last node, instead of pointing to null, points to the first node in the list. So this is a circular linked list. And similarly as before, the first node of the list is referred to as the head, and we also keep a track of the last node, which is referred by the tail pointer. Now these are the standard variants which you might see, but there are many other variants, like there's a circular doubly linked list in which the last node points to the first node and also each node stores reference to the previous node. Anyone can make modifications according to their whims and fancies, so there can be multiple variations possible, but these three are the standard ones. Now to understand the operations and code, we need to have a good understanding of pointers. So here is a very quick refresher on pointers. Just in case if you're not coding in C++, so feel free to skip this section because this might not be very relevant for you. So pointers are nothing but variables that point to a particular address in memory. So let's say that we have a memory cell which has an address ABC and it stores a value 10. Then a pointer, instead of directly storing the value 10, will actually store the address of that cell and will be pointing to that cell. So let's say that the structure of our class for node looks something like this. So here we are obviously storing the info or the data in the node. We also have a pointer next. So this next pointer is actually pointing to an address where we have stored our next node. And since the data type stored in the address is of type node, that's why the type of this pointer is also node star. So we have made a pointer of data type node, which is going to point to the next node of our linked list. So our linked list would look something like this. So let's assume that this is our first node and this is our second node, and there is some data, say 10, and there's data 20. So next will be equal to the address of the next node, so it will look like this node is pointing to the next node. And let's assume that this particular node is the last node, so next in this will be equal to null, because this node will not be pointing to any node since this is the last node. So this is how our linked list would look something like. Also, when we write this statement node star pointer equal to new node, what we are doing here is that we are first creating a new node, or we are first constructing a new node, and the address for this particular node is getting stored in the pointer ptr. So this is something like, this is the node and ptr is actually pointing to this node. So now let's try to understand the insertion and deletion operations in the linked list. So let's first try to insert an element in an empty linked list. So when the linked list is empty, the head is obviously equal to null because there's no node and head is not pointing to anything. So what we do is that we initialize a new node with data and ptr is pointing to this new node. Now what we need to simply do is that since this node is going to be the first node in our linked list, this node is the first node in our linked list, so our head should also point to this new node. So what we need to do is that simply we need to write head is equal to ptr. So what will happen when we make head equal to ptr, head will also start pointing to this node. So that's how we have inserted an element into a empty list. Now let's look at the case where we want to insert an element towards the end. So our list is not empty, and let's assume that our list looks something like this. And we want to insert an element in the end. So what we need to do, simply we first need to create a new node. So let's say our new node has been initialized. And what we do is that we start traversing from the start of the list, and we reach the last node of the list. And what will be the identification for the last node? So last node will always be pointing to null. So when we have reached a node that is pointing to null, we know that we have reached the last node. So when we have reached the last node, what we need to simply do is that the last node, instead of pointing to null, should start pointing to the node that we have just declared, and this new declared node will point to null. So by just changing the value stored in the next data member of the last node, and by making it point to the new node that we have created, we have actually added a new node in this linked list. Now let's try deleting elements from the list. So in the case where we are trying to delete an element from a list which is of size 1, so there's only one element in this list, and this element is obviously pointing to null, and the head is also pointing to this element. So to remove this element or to make this list empty, we need to do nothing but simply make head equal to null. When head is not pointing to any element, we have made the list empty. Now let's try to delete an element at a particular index in our linked list. So let's say our linked list looks something like this. And let's give each node an index. So this is 0, 1, 2, 3, 4. Now we want to delete the node at third index. Say we want to delete this node. So to delete this node, what we do is that we take two variables to traverse this list. One is the current pointer and the next is the previous pointer. So the previous pointer always points to a node behind the current pointer. So when current pointer starts from the first node, the previous pointer points to null because there is no node behind this behind the first node. When current pointer moves to the second node, the previous pointer moves to the first node. Similarly, when current pointer moves to the second node, the previous pointer moves to the first node. When current pointer moves to the third node, the previous pointer moves to the second node. And we stop once our current pointer has reached the index that we want to delete. Now to delete this node, what we need to simply do is that we need to take the node which is being pointed by previous. So in this case, the node being pointed by previous is this node, and we need to change the reference of this node, and this node should start pointing to the fourth node. So when this node starts pointing to the fourth node instead of the third node, what we have done is that we have simply removed third node from this list. So now our list looks something like this. So when we'll start traversing this list again, we will be at 0, then we will go at 1, then we will go at 2, and we will directly go at 4. We will never come at this particular third node. So we have deleted this node from the list by simply changing the reference stored in second node. When we change the reference in the second node to fourth node instead of the third node, we have actually deleted the third node. So now let's quickly go through the code for these operations. So the first thing that we do here is that we have defined the node class. So as we have already discussed, our node class has two data members. One is data, which is going to store the info in the node, and second, we have a pointer to the next node in the linked list. And then there are two constructors in this node class. One is a default constructor which initializes data as 0 and next as null, and second is a parameterized constructor which initializes the data with the value that has been passed as input to the constructor, and again the next is initialized as null. After the node class, we have defined the linked list class. So the two main components of linked list class is the head node. So we define a linked list by head because head is always pointing to the first node in the linked list, and we also have a data member size. So this size is going to store the total size of the list. Now there's a default constructor for this class because it's mandatory to define a default constructor. So in this default constructor, we have initialized head as null because when the list is empty, head is equal to null and size will be equal to 0. Now this is the method which is responsible for inserting values in a list. So it accepts in data as the input. In data is the element or the value that needs to be inserted in the linked list. So first what we do is that using this data, we create a new node. So we have created this new node, and the new node pointer is actually pointing to this new node that we have created. Now first is the case when list is empty. So when list is empty, head is obviously equal to null. So as we have discussed previously, we just make head equal to this new node pointer. We increase the size by 1 and return. So by doing this, we have inserted the first node in the linked list. Now in the case when linked list is not empty, in that case what we do, we create a helper variable travel. Obviously travel is going to point to the first node, so it is also of the data type node star, or it's a pointer or to the data type node, so it has to be of type node star. Now using this travel variable, we are going to travel the linked list. So how we are going to travel the linked list? So let's say that this is our linked list and travel is currently at this position. Now if I do travel equal to travel of next, so the travel of next is this node, because travel is so the travel of next is actually this node, because travel is currently pointing to this node. So if I store travel of next in travel, what I have essentially done is that I have moved travel by one step and travel will come here. So by this statement, travel equal to travel next, I am actually moving travel ahead. And the condition for stopping this while loop, so as we discussed that we want to reach the last node of this linked list. So last node is always pointing to null. So when I have reached the last node, I can identify this last node, that if the value stored in the next of this node is null, then this is the last node. So that is what the stopping condition in my while loop is, that if the value stored in the next of my current node is null, then this is definitely the last node. So when I've reached the last node, I break out of this loop. What I do is that this last node should now point to my new node and not point to null. And if it points to my new node, I have actually added this new node into the list. I increase the size by 1 and I return from this method. Now let's discuss the delete node method. So in this, the delete node method obviously accepts an index. This index represents the index of the node that needs to be removed, and it is a zero indexed list. So first is the case where we try to check that we have given a legit index. So if the size of the list is 0, then obviously we cannot remove any node. Or if the index given is greater than equal to size, then the index given is out of bounds. So in both the cases, we do not do anything and return from here. If the size is equal to 1, when there's only one node, we have already discussed that we simply make head equal to null. And by making head equal to null, we have lost the reference to the first node. So now the list is empty. We decrease the size by 1 and we simply return. Now in the case when the list is not empty, what we need to do is that, as we discussed, we keep two pointers. One is previous and one is travel. So travel is the current node I am standing at, and previous is just a node behind the current node. And I also initialize the index of the current node, which is 0, because I am starting from the first node which has an index 0. What I do is that I keep moving my current node till I have reached the index of the node that needs to be removed. So in each step, the current index is being increased by 1. So when my travel pointer, which will reach at the node that needs to be deleted, my current index will become equal to index. So that is the point where I actually need to jump out of this loop. The second condition is actually making sure that we do not go outside the linked list. But since we have already checked in our first condition that the index given is not out of bounds, so this condition will never get hit. So we could have actually removed this condition just by putting current index less than index. We would have it would have worked fine. So what we are doing here is that we are in every step we are increasing the current index by 1. First we are making previous equal to travel, so we are moving previous by one step, and then we are moving travel by one step. So in every step, both previous and travel are increasing by one step. And finally, when my current index becomes equal to the index of the node that needs to be deleted, I jump out of this loop. And what I do here is that, so we have already discussed, to delete a node, say I want to if I want to delete this particular node, previous would be and this node. So what I need to do is that I need to simply change the reference stored in this node, and this node should start pointing to this node. It should skip the current node. So what I have done, so in travel, next of travel, basically next of travel will be this node. So what I'm saying, that previous of next should start pointing to this node. So the value stored in the next variable of previous, which is this node, should be the value of this node, which is next of travel. And I also free up the memory taken by travel node. So I call the delete keyword and I remove this node from the memory. So by doing this, I've actually skipped this node in the linked list and I've also removed it from the memory. In the end, we decrease the size by 1 as we have deleted the node and return from this method. The time complexity for both insertion and deletion operations is actually big O of n, where n is the size of the linked list. So the time complexity is linear because in insertion we are trying to insert an element towards the end. So every time we try to insert an element, we have to traverse the complete linked list, which takes big O of n time. And insertion is an O1 operation. For deletion, the worst case is big O of n, because the best case is that we want to delete the first element. So that is a O1 operation. But when we are trying to delete the last node of the linked list, in that case we would have to traverse the complete linked list, and then deletion would be a O1 operation. So the worst case time complexity for both insertion and deletion is linear and it is big O of n. The space complexity for both the operations is big O of 1 or big O of constant, because we are just using a helper variable or helper pointer, so the space taken is constant. Finally, like any other data structure, linked list is also pre-implemented in most of the languages. Like in STL, we have the list container, which is a linked list behind the scene. So the template for list container looks something like this. So if we want to declare a list for integer, the declaration would look something like this. So people often wonder the difference between list and vector. So the difference is just this, that list behind the scenes is a linked list while vector behind the scenes is an array. So with this, we have reached the end of this introductory video. Make sure that you have completely understood everything discussed in this video before actually moving on to the practice problems. In case there is any doubt, do post in the comments below and I'll try to answer all your queries. As usual, this video is necessary but not sufficient to become proficient. So do practice problems after watching this video. And we are also going to solve some LeetCode problems on linked list in subsequent videos. So stay tuned. Thanks for watching everyone. Stay safe and keep learning. See you in the next video. Bye bye.